Welcome to another video explaining the universe using the particle model. The title of this video is a bad example for G2 gravity. Turns out I used G1 gravity to help support the idea that you needed a G2 gravity. But first, a word about the book. Dave and I wrote a book, and you can buy it on Amazon in hardcover, paperback, or ebook. Well, it turns out that John Walker, a consistent follower of mine, wanted a copy of the experiment with 3 balls. I made that up and did not review it properly. Yeah, it was a big mistake. You think you're doing right, and it's still wrong. So this is a slide he was asking about. He wanted an explanation of, or an explanation of some data that supported this test. And this is Newtonian gravity, and I'm using G1 Newtonian gravity. Actually, I'm using G2 gravity to support this idea of G1 gravity. Well, it turns out that David Scott, the astronaut, did the same experiment on the moon. The hammer and feather hit the ground at the same time. And I have made a video on titled Hammer and Feather. So if it hits at the same time, this is the drawing I made. I didn't get it on the internet. I didn't find it in some experiment. And yes, the top drawing is mine. I drew it and did not think it through. Now, G2 gravity controls the bending of light. And my drawing might be correct if each ball went through a different medium, but it doesn't. And so, according to Galileo, the balls should hit at the same time. No matter the fact that if you apply the same force in the same direction, they fall at the same time, they're going to be in the same spot. So let's take a look at one of the things I maybe should have thought through is the force gradient. Here's the force gradient for a prism. To bend light, the G2 gravity, that is F2, is perpendicular to the edge. And you can see over here it's kind of small. There's a F2 force, which is the net G2 gravity on the edge of the perpendicular to the edge. The strength of the F2 force is based on the G2 mass where the light enters the prism. So here's a force coming out, and it's perpendicular. Both are perpendicular, and this is the net G2 force of G2 gravity. The strength of the force is based on the mass where the light enters the prism. And here, this light enters the prism, and it has a larger mass than this light, which enters the prism, and hence the net G2 gravity force here is smaller than here. The strength of the F2 force is based on the G2 mass where the light enters the prism. It is the G2 mass that causes the force gradient. Okay, force gradient on balls. Well, when Galileo did his experiment with 2 balls, there was a force gradient, and it's dominated by the Earth. And it's equal in all directions. It has nothing to do with the 2 balls he was dropping. So the Earth dominates the G2 force, which is the net G2 force is F1. So there is no G1 force gradient. The balls will fall in the same place, just like Galileo's experiment. Well, so if there was no force gradient, maybe we can develop a model where the force gradient is different. And the only one I could come up with is an experiment which would be extremely difficult to do, but at least it's conceptually possible. Uh, Galileo's experiment with the Earth having a force gradient that is equal somehow, if it's not the force gradient, then maybe it should be the drag that I should have picked as my example for supporting G2 gravity using G1 gravity. So we tried different mediums. This is not easy to do, but I'm suggesting that someone stand at ground level and where there is strong drag and go up to a higher level, like in a hot air balloon, where you'll get lower drag, and then finally in outer space where there is no drag. So if you throw a ball at ground level, it's not going to change its path due to the F2 forces or F1 forces. It changes its distance by the drag of the medium. You throw another one at the high level with lower drag, and in outer space there's no drag. Obviously, that's very difficult to do. It's conceptual, and you end up by going through different mediums. On the ground, you get strong drag; it'll drop first, and at a high level, you have lower drag, and it'll drop next. And in outer space, no drag at all. G1 gravity will push each ball down to the Earth. Just like I showed, G1 gravity has equal forces. There is no gradient. Ground level, lead ball drops first. High level, wood ball drops next. Outer space, maybe it never drops. My name is Bob D. Hilster, and I want to apologize for the mistake, but I hope that you enjoy the videos that I make anyway. If you have a question, ask Particle.